Now that we have a way of getting a bunch of examples of orthogonal complements, let's see what useful properties orthogonal complements can have. First of all, remember the rank-nullity theorem? This theorem, we took a matrix, looked at its rank, which is the dimension of the row space, and its nullity, which is what we named the dimension of the null space, and we said that those two numbers add to the number of columns of the matrix. Here in theorem 5.2.2, we'll see that this is true for any subspace and its orthogonal complements. Though in this case, the number of columns is replaced by the dimension n of the Rn that we are working in. In fact, this will actually go a little bit further, and it will tell us a way of getting a basis of Rn from bases for our subspace and its orthogonal complement. I'm not going to go through the entire proof of this, but we're going to at least prove the first part. When we prove this, we do have to first deal with one special case. This case where S, our subspace S, just consists of the zero vector. In this case, because everything is orthogonal to the zero vector, that means that S perp is actually the entirety of Rn. The dimension of just the zero vector is equal to 0, and the dimension of all of Rn is, of course, n, and so if we add these together, we do get n. So dimension of S plus dimension of S perp is definitely n. Not too bad, but we have to treat this one a little bit differently than we're going to do the other ones. If S is not just the zero vector, then let's say that we have a basis for S. Let's call them x1 through xr. So we're saying that this is a basis, so they're linear independent, and they span to S. Of course, we're saying here the dimension of S is R, because that's how many basis vectors we have. Let's use these x's as the rows of a matrix. So we'll have an A. Its first row is going to be x1. Well, it has to be x1 transpose, because we're going to say these are column vectors to begin with, and now we want them to be rows. So x1 transpose all the way through xr transpose. This is a matrix. It has row space of S. So actually R of A transpose equals S, just by construction. And it also means that its rank, the rank of A, because it's the dimension of the row space, and the row space is S, which has dimension R, then the rank of it is R. What about the null space? Well, because we have the result from the end of the last video, where the null space is, in fact, the orthogonal complement of the row space, we can actually find what those are. We're going to look at S perp. S perp is just going to be, well, S is the row space, so this is the row space perp. But from our theorem, this is actually just the null space of A. And so we actually can write, we've written down S perp as a space that we might be able to work with. Well, what is the nullity? Or maybe we'll just write null of A. I think that's what we were doing before. What is the nullity of A? Well, we have the rank-nullity theorem. The rank-nullity theorem says that the rank plus the nullity has to equal n, because n is the number of columns here. Remember, each of these vectors is in Rn, so each of these rows is n elements long. So there's n columns. The rank was R, so the nullity has to be that difference, n minus R. Or we could just write it so that the rank of A plus the nullity of A is equal to n. Of course, the rank of A is the dimension of R of A transpose, or the nullity is the dimension of the null space. So we can just put those in there. But then the row space, as we've already said, is S. And the null space is S perp. And that's the first statement of our theorem, that the dimension of any subspace plus the dimension of its orthogonal complement is in fact the dimension of the entire space. The details of the rest of the proof, of talking about the bases, that's a little bit messier. If you're curious, it's laid out in the book, but I'm not going to go through that part. But the idea of how being able to work with two different bases, working with the basis from S and the basis from S perp, and combining those to get a basis for the entire space, the entire Rn, is actually pretty useful. We can actually rewrite this as saying that any vector in Rn can be written using a vector S, or a vector u from S, and a vector v from S perp as a sum. X can be written as u plus v, and in fact there's exactly one way of doing this. You can think of it as x can be written out in terms of the basis for Rn, where some of those basis vectors come from S, some of them come from S perp, and we just group up the ones that come from S and the ones that come from S perp and call those u and v. So not to get into too many details there, but being able to essentially decompose x into part that comes from S and part that comes from S perp is something that we commonly like to do when we have subspaces of a vector space. So we're going to give a name to this concept. We'll say that if u and v are subspaces of a vector space W, and every w in or little w in W can be written in a unique way as a sum of a little u from U and a little v from V, then we say that W is a direct sum of u and v. And in a way, we're adding together vector spaces, which might seem a little bit weird, but this is what it means. We're able to add things from each of the two vector spaces together, the two subspaces together, to get any vector in their sum, in their direct sum. We are going to write this in this way, that W is U with a plus sign in the side of a circle. Sometimes people say O plus, and then V. Or I'll probably just say the direct sum of U and V. And then everything from the last theorem can kind of be summarized, or at least the last part of the last theorem can be summarized as if S is a subspace of Rn, then Rn is the direct sum of S and S perp. Again, I'm not going to go through the details of the proof, but they are in the book if you want to go through them. We're going to end this section with one last result. You probably would have guessed this one already, but just by the way that I've been talking about it, that a subspace and its orthogonal complement kind of come as a pair of complements, that they're complements of each other. This is definitely the case, but it actually takes a little bit more work than you might think to prove it. But that's why we didn't do it originally. We're going to be using some of the stuff that we've been using up till this point. Now, it's not too hard to see that everything in S is orthogonal to everything in S perp. I mean, that's part of our definition. So it's actually pretty easy to see that S is at least a subset of the orthogonal complement of S perp. But whether or not S is the entirety of the orthogonal complement of S perp is a little harder to see. That's why we're going to actually use the previous theorem, theorem 5.2.3, to show that that's the case. That everything in S perp is actually already in S. So let's assume that Z is in S perp. So Z is definitely orthogonal to S perp, but what we're going to make use of is the fact that it has to be an Rn. And Rn is the direct sum of S and S perp. That means that there's a U in S and a V in S perp. In fact, there's unique U and V, where Z is equal to U plus V. Let's take the scalar product of Z with V. So V transpose Z is equal to V transpose U plus V transpose V. But what is V transpose Z? Z is in the orthogonal complement of S perp, and V is in S perp. That means that Z has to be orthogonal to V. So this is equal to 0. But what is V transpose U? U is in S, and V is in the orthogonal complement of S. So they have to be orthogonal too. So we have a 0 there. What's V transpose V? Well, that's just the magnitude of V squared. But what is this saying? This says that 0 equals 0 plus the magnitude of V squared, or in other words, the magnitude of V is 0, meaning that V has to be 0. That's the only thing V could have been. And so what is that saying? That means that Z is equal to U, but U is in S. So Z is in S. Everything that was in S perp has to be in S. And since everything in S we already knew that was in S perp, they have to be the same thing. So that's all we need to have. Now, that does allow us to turn our theorem 5.2.1 said that the null space of a matrix is equal to the row space, or R of A transpose perp. And then, of course, we also have the similar thing if we just switch A out with its transpose. We have that. But now, because we can actually say that the orthogonal complement of an orthogonal complement is the original space, if we take the orthogonal complement of A, or of n of A, the null space of A, this is just going to be the row space. I keep mixing up my T's and my perps. Same thing over here. So you can see here that we can essentially just move the perp over to the other side, and it doesn't change anything. And that allows us to do various things. We'll talk about these, especially in the next section. The next section actually uses this idea in order to solve some problems that look like they shouldn't have any solutions by finding solutions that are in some sense close enough, or the closest possible solutions. I'll talk a little bit more about that when we get to that section. But it's a very, very useful idea. And there's a few other consequences that the book does go through. Corollary 5.2.5 details how we can think of part of a vector that is orthogonal to the range of a matrix. well, I'm not really going to get into that too much right here. I feel like some of this other stuff that they do in the section is a little bit of a side results, and I'll leave you to read those on your own. We're not going to need them for anything that we're going to be working on, and you won't need them for the homework, but they might be interesting reading. But I'm going to go ahead and leave it there. Kind of rambling on maybe a little longer than I wanted to anyways with this video and the previous video, and I do want to get to some examples so that you can kind of get an idea of what to expect on the homework. So I'll leave it off for now, and I'll see you in the next video.